Hey kids, Smath here. Third installment on colligative properties, and this one should be our last one. This one we're going to do one where we have a substance, ethylene glycol, commonly used in antifreeze, keeping cars from overheating or overcooling. And we're going to use that in something that's not water. So we're going to have some different values for KBKF. And then I have two examples for you where we can actually use colligative properties to calculate the molar mass of a substance. This is just like we did when we were using the ideal gas law and calculating the molar mass that way. So this first problem wants us to use both the boiling point and the freezing point, but we've got 6.5 grams. So I'm going to get a little space over here. And what we have is 6.50 grams of this ethylene glycol, C2H6O2. When always, I don't know what to do with the problem. I'm kind of lost. I'm not sure. Always turn it into moles, 62 grams. This is going to be 0.105 moles. Now that moles is actually in 200 grams of our CS2 as a solvent. And so this is 0.2 kilograms. And so if I use that, the molality of this, 0.525, molal. We could also write it out, molal, doesn't matter, okay? But it wants to know what's the boiling point and what's the freezing point of this solution. So I'm gonna come back and I've looked on the front at the top of the page here and it told me that the KB, so I'm gonna do boiling first, delta TB was KB 2.34. Hey, wait a minute. Why isn't it 0.51? Well, 0.51 is for water only. It's not for CS2. So now we're going to use the constant for CS2 and the boiling point for CS2. So in this case, my molality, 0.525, excuse me, 0.525. And C2H6O2, pretty carbon-based, so I'm going to deal with 1. That's going to give me a delta T of 1.23 degrees Celsius. And now, since this is boiling, I can look at the top of the page and find out the normal boiling point of CS2 is 46.2. So this is going to increase it to 47.4 degrees Celsius. My boiling point still increased, but it didn't increase from 100. It increased from the normal boiling point of 46.2. Now let's take a look at what happens with the freezing point as I come over here. So delta TF now is 3.83. Still 0.525, still 1, but now my change is 2.01 degrees Celsius. Now we're not going to subtract that from 0. Instead, I'm going to look up at the top of the page and find out what's the normal freezing point. Well, normally the freezing point's negative 111.5 minus 2.01. That's going to make this negative 113.51 degrees Celsius. Still just subtracted. So that's what we do when it's something that isn't water. We've got to go back to the beginning, look it up, find out the KB, find out the KF, find out the boiling point, find out the freezing point. We've got to be given all that information. And then all we do is plug it in to KBMI, KFMI. Now, how do we use these? Here's two examples where we can use this type of problem to solve for molar mass. Molar mass, remember, grams per mole. Okay, so we've got a 1.5 gram sample of urea. Well, what's urea? We don't need to know that. We're going to look, we're going to determine, calculate the molar mass. We're not going to look it up on the periodic table. We're going to calculate it from the boiling point data. What they told us was that this was in water and it boiled at 100.12. So what that tells me is that delta TB is 0.12 degrees. How did I get that? Well, it normally should boil at 100. So now it's boiling at 100.12, 0.12 difference. Okay, so that's my delta T, and that's equal to the KB, 0.51, M, and I don't really know. They didn't say anything about it. They're saying molecular mass, so I'm just going to have to assume I is 1 unless they told us that it split into a certain number of particles. So if I solve this, the molality of this solution is 0.235 moles per kilogram of solvent. And we were given in the problem 105 grams. So let's bring that down, times 0.105 kilograms. I just slid the decimal over 3, okay? And that's going to be equal to 0.025 moles of urea. Now remember, at the beginning of the problem, we were asked for molar mass, grams per mole. Well, they gave us in the problem 1.50 grams in 0.025 moles. And if I let Texas Instruments lift that, I get 60.7 grams per mole. That's my molar mass. We're done. You use the change in temperature to calculate the molality. You multiply that by the kilograms of solvent. That gives me moles. And then I divide that mass given to me in the problem, the 1.5, that's the mass, divided by the moles that I calculated, and I get a molar mass. Let's do another one of those. Here we got a 5.5 gram sample of something. I'm going to use that 5.5 at the end. In this case, it was still in water. Nope, this is in pure benzene, but they gave us the change in temperature. They said that it was found that the freezing point of the solution was 1.02 below that of the pure. So that is my delta TF. So delta TF is 1.02 degrees. That's equal to the K right there, 5.12. M is what we're looking for, and we're just going to have to assume M is 1. You should never have a problem where I, in these molar mass type of problems, isn't 1. So if this is the case, my molality is 0.199 moles per kilogram. Okay? How many kilograms of solvent did we use? Oh yeah, they told me up top it was times 0.250 kilograms. So my moles aren't very many, 0.498. That's the moles. Remember my 5.5? No problem. Molar mass, 5.5 grams over 0.0498 moles, grams per mole. Looky there, I'm going to get a mass of about 110 grams per mole, just what I was supposed to get. So we're just using the change in the solution's freezing or boiling point, colligative property calculation, and then finding out how many moles, dividing the mass given in the problem by the number of moles that we calculated. These solutions are going to be up online. I'm Smath. I hope this video helped you.